You had some work I asked you to do in the counting unit over the weekend. And I only have one guideline for you, and that was, when you got confused, stop. Now, you may have managed to get through the entire unit, and if you did, that's fantastic. If you hit a point at which you had to stop, that's okay. So where did we hit the point that some of you stopped, if any? Or did everybody just zoom on through it? Okay.
4 pages in.
4 pages in. What page was that?
When you start 100. I'd say problem number 5, I think. Page 8 is where I stopped.
Okay, so page 8 is where I'm hearing, which is just before number 5. This is where you're rearranging stars, correct? And we had 34 stars to start, and we were asking in this problem to rearrange them in groups of what on problem 3? There's the statement. So rearrange the 34 stars into groups of 4, right? Okay, that's where we're going to go. So let's start there. And this may not have been where you stopped or had trouble, but this is where I'm going to go with it. 34 stars. There's nothing very exciting about doing this, but it's a place we really need to start. But I am going to add a little addendum here. Now I know I have 3 groups of 10 and 4 to the right of that, but I'm trying to keep things centered in the board a little bit better, and it looks like I went uphill a little bit. Just a reminder, we're in base 4. What are your place values? In base 4. Place values.
1, 4, 1, 4, 2.
Always starts with the ones, always, first digit on the right. It always goes to what on your second digit? The base. So that's going to be a 4. Always. Then what do I do to get the next place value? Multiply by the base. Not doubling, but multiplying by the base. So 4 times 4 is going to be 16, although you could argue it's 4 to the second. And this is 4 to the first. And this is 4 to the 0. So you can do it with powers of 4. What is my next place value? 4 times 16, which will become a 64. Just keep that in mind. Now I started with how many x's up here? 34 of them. Hint. The largest place value I could have is 16. Couldn't have 64. So here's a nice shortcut after you've done the unit or worked on it. Let's divide 16 into 34. Let's see what we get. We get a 2. Agreed? I heard that given by someone. So I have 2 groups of 16. Agreed? Now what do I have left when I subtract? A 2. Can I have any groups of 4? My answer, 202. Let's see what happens when I group up here, the way I expected you to do it. I wanted you to take groups of 4. There's a group of 4. Here's a group of 4, agreed? Here's a group of 4. Here's a group of 4. Now I'm supposed to group by what? By 4s. I have 4 4s. So I do what? Group those together. That's my one group of 16. Then I have what? Group of 4, group of 4, group of 4, and what? Another group of 4, and that's 4 what? Again, 4 groups of 4. So I have a group of 16 here, group of 16 here, and what left? 2. There's my 2 groups of 16, 0 4s, and 2 left over. Now I wanted you to do it by actually drawing little boxes and regrouping 4 boxes of 4 into a group of 16. But here's a nice shortcut for doing the same thing, dividing by the highest place value I can, which is 16. Does that answer the question on that problem? Okay? Okay, anybody else? Did everybody end up stopping at about that point? Page 8. Did anybody else have another question a little bit earlier than that? Okay. How many of you managed to get to question 5? This question. Okay, 1 of you? That's it? 2 of you? This is 3 of you? 4 of you? Let's see if we can work 5 of you. Good. So 5 on 5. Okay, let me ask you this question related to that. What digits do we use to write a number in base 10? What digits do I use? So I'm in base 10. What digits do I use? And I heard one of you say this answer. Now this is one of those questions and answers that most people don't really understand as well as I'd like. We have 10 digits. We call our system base 10 because we have 10 digits. Do you see a 10 in those numbers I wrote down? And the answer is no. 0 through 9 are my 10 digits. When I get 9 and add 1 more, I say I have 1 group of the base and nothing left over. And that doesn't seem to internalize as well as I'd like, because when I come to this question, suddenly there's a problem for people. They don't understand this question as well as this. The digits we used, and we did this problem on Thursday, it's 0 through 4. We have how many digits? 5 digits. You're in base 5. The base tells you how many digits you're going to have. Now when I get to the base, how do I represent it? 1 0. 1 group of 5, nothing left over. I don't read this as a 10. I read this as 1 0 or 1 0. So I read as 1 0. Let's go to base 3. How many digits will I have if I'm in base 3? 3 digits. 0 counts, okay? You're thinking of 1, 2. But I can have a 0. 0, 1, and 2. Now how do I represent 3 of anything? 1 0. Now let's go back and look at problem 5. Write the digits used to write numbers in the base, and then it says write the number we use for the base itself. So you could now do A and C, correct? You could fill those in if you haven't done that already. Because in part A, base 5, you would write 0, 1, 2, 3, and 4, and then you write the base itself as 1 0. Okay, so that gets us up through question 5. There are only a few more questions. The problem we did in class, which was to count in base 5, this is what we tried doing in class with pennies, pennies, nickels, and quarters, where we did 1, 2, 3, 4, 1, 0. That was page 11, and that forces you back to where we were on Thursday. So here's the agreement. You stopped when you should, that's fine, but now you should be able to do a little bit more. Now this is a short week, so I'm not going to spend Thursday on the counting unit. I've tried to spend some time this morning answering a few questions about it. However, relative to what you need to do this week, I'd like you to continue working at the point where you had trouble. Don't go any further than that, just keep worrying about that. Now notice I say keep worrying about that. Because if you keep working on it, what am I gambling on? That at some point, it'll hit you. Driving the car down the street, eating dinner, waking up in the middle of the night, but at some point, you'll have that aha moment and say, oh, I've got it. Now, one of the things that is a very classic response, and it's something that one of these students in the last hour shared. The young lady said that she'd asked 5 people to read the unit up to the point where she was having trouble, and everybody had trouble with it. That makes sense. Take the calculus students, taking 171, ask them the same question, and they'll have trouble with it. Because most people have not thought about what it means to be in base 10 or go to a different number base. Now, where do you have to know this stuff? Sort of a George Carlin kind of thing. This is stuff. If you take an introduction to computers, base 2, you'll cover it there. And I hope everybody is planning to take some kind of course where you feel comfortable using a computer and understand what's going on there, because that opens so many doors. But aside from that, understanding base number systems is important, I believe, just in your backgrounds, because you use base 10 all the time. Now here's a very classic response I have from students when they finally get it. And they do. This is not what makes the difficulty for Math 10. Contrary to what you're probably thinking, this is going to do me in. No. Students do get this. It just takes some a little bit longer than the others. And we spend lots of time on it. So people do get this unit. And here's what they say once they get it. If somebody else asks them, oh, it's easy, let me show you. Once you get it, it seems as easy as can be. Until you get it, it's the hardest thing you probably have done recently. That's the difference. Now, going back a whole lot of years, there was a mathematician, comedian. Okay? His name was Tom Lehrer. And you can still get CDs of his, and he still publishes music. But he said in a parody he did, and he worked at nightclubs doing a parody about this unit. He said, it's so simple, and he was doing a problem in base 8. It's so simple that only a child can do it. And there's a bit of truth to that. Because as an adult, you bring what baggage with this? Base 10 is what you've been using all your life, and that's where your head is. And I'm asking you to see a 1, 0 and not call it a 10. And it's hard for an adult to do that and let go. It's easy for a child. If I start with a child who doesn't know anything about adding, counting, they'll learn base 5 just as fast as they learn base 10. Once you've learned that base and go to another one, it what? Rattles your head. Makes it a little bit frustrating. And you fight it. But you will get it. Okay? It does work. Now, one of the interesting results out of this, and when I wrote the curriculum for this course and wrote the first books, I had no intent that it have a follow-up course of Math 20. I saw it as an alternative, Math 10 or Math 20. But we've reached a point where everybody needs that algebra background. So 20 is a pre-algebra, 70 is the algebra course, then a 90, and that opens doors because it means you can take a 100 level course and continue your education into 4-year school. that changes lives, it's opening doors, and that's what's important about it. So when I wrote this, the intent was just to do some reviews. We're just going to stay with arithmetic. And in doing that, my choice of units had a different intent than where it is now. This Math 10 makes Math 20 a whole lot easier to do. The biggest problem has been to get students to get into Math 10. I'd love every single math student at this college to take Math 10 so that they could do the arithmetic they need to do, know how to do it, and learn some other things that are important. But we only run about 4 or 5 sections, and we need probably to have twice as that many for the number of students who really need to be able to sit down and understand the number system. So if you're trying to deal with this, be patient with it. It does work, and for the most part, you find that if you ask for other people to help you, they're going to have the same problems you're having. What's the best way of understanding this? Explaining it to the refrigerator door. It works. The refrigerator door learns a lot this way. Okay, but it does, I think that's the secret to it. Explain to someone else. And when you do, if there's still a glitch, you'll then realize what it is. So I'm not asking you to do any particular number of problems, just don't let this go. You ever see a puppy chew on one of those bones that you buy at the store for them? They're sort of like out of rawhide, and they just keep working on it and working on it. That's a little bit like what I want you to do with this unit. Keep working on it. No matter how rotten you feel about it, it will work. If you don't work on it, there's no hope of it working. Any other questions on the unit? That's the counting unit. Orange book. Okay. Let's come back then to the computational review. Now this week, we're going to, and I, by the way, have returned the review test 3 to you. I have a few more of them up here. If you came in a little bit after they were returned, just pick those up at the end of the hour. There is no test that was due today. Nothing from the orange book. Just get as far as you can, and we'll continue with that. Now we're going to go to lesson 4. Now this is where we notch things up just a little bit, because in lesson 4, I'm asking you to deal with multiplication. So Debbie, since I have some things over on that other board, we'll go to there next. I'd like you to bring up that multiplication table I have at the bottom left-hand side, and just bring that into the screen, and then I'll walk over there once you have that. Multiplication, there are certain things that you're supposed to have learned as a kid, and most of you probably are pretty comfortable with what I have on the board. This is the multiplication table for 5s. It goes 0 through 5 in the top, 0 through 5 here. Okay? And I think you know the drill. If you want 3 times 2, you go to the 3, you go to the 2. So you bring the 2 column down, you bring the 3 over, and you say 3 times 2 is 6. My guess is that this part of the multiplication table is pretty darn comfortable for you. Not really a hassle. It's when the numbers get above 5 that you have trouble. By the way, I'm going to do an addendum here, Debbie, that I didn't do in the last hour. Let me put that same table up at the top, but we're in base 5. Okay, let me write it for you. Base 5. I'll just take it to the 4s. We're in base 5. Okay, so 2 times 2 is still 4. But what's 3 times 3 in base 5? 3 times 3 is a 9. That's 5 and a 4. 3 times 3 is 9. How do you write a 9 in base 5? How many nickels and pennies?
1 and 4.
1 nickel, 4 pennies. So this is a 1, 4. Okay. Let's try 4 times 4. Base 5. Get a 16. How many nickels and pennies? 3 nickels, 1 penny. So 4 times 4 is 3, 1 in base 5. That didn't go over well. We don't have dimes in base 5. We only have pennies, nickels, and quarters. So if you want to play with another base right now, try a multiplication table in that base. It's interesting. I think I'll leave that before I create hostility. Okay. Let me look at this special set of numbers in my table. What do we call these? We have a name for them. Okay, the 2 is an exponent each time. But what we call it when I say a 5 squared or a 3 squared? We have a name for that group of numbers. Perfect squares. And that's really where we focus. Now, I have many of those. I guess I have all of them in my table, correct? Because 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Remember, this exponent tells you that you have a 3 times a 3. This exponent tells you have a 4 times a 4. So these are our perfect squares. And as I say, I find that most people are really comfortable with multiplications as long as the numbers are 5 or a little smaller. This is where life gets more intriguing, challenging. Okay, 6 squared. 36, agreed. 7 squared, the 49ers, San Francisco. Now the 8 squared is a little bit harder for many people. It's 64, and the 9 squared is 81. Okay, those are my perfect squares. Now those numbers become helpful to me if I know them. So for example, here's a problem that drives a lot of students to a calculator. They see an 8 times a 7, and they immediately want to use a calculator. But if you know your perfect squares, and down here I have 7 times 7 is 49. 8 sevens is just what? 7 more than 7 squared. So I know this is going to be 49 plus 7. I can do that in my head and get 56. That's the shortcut that we may take to remember something that's hard to remember. What about 7 times 6? What would you use here for your shortcut if you don't have it memorized? Okay, I could take 6 squared, that's 6 sixes, that's 36, and add one more 6 and get 42. What's another approach? I have 7 sevens, 49, so I can take the 49 and subtract 7 and get 42. Still get the same answer. That 4 didn't look very good. Get the idea? Now, most of the time, that's not where the difficulty comes. It's with these. The 9s really bug people. Okay, that's where much of our difficulty comes. Okay? So, what I'm going to do is look at these 9s, and before I do that, just a comment. because I need to come back to this. We're doing multiplication, so these answers are products. And I just have up here for you that when we added, we had sums. When we subtracted, our answer was a difference. When we multiply, it's a product. And it will be, very quickly, a division problem tomorrow. And our answer will be a quotient. So the question, how do I handle nines? Because if I can handle the big numbers, the small ones are pretty straightforward. Here's the shortcut for nines. Now, most of the time, I find this is new for students taking Math 10. If you've learned this before, I'd be interested to know, because I don't find very many people use it. 9 times 8, my shortcut is this. Take the 8 and drop it by 1. That gives me a 7, correct? What do I need to make 9? 2. That's my answer. Okay, let's do 9 times 7. What am I going to do to the 7? Drop it by 1, getting a 6, and add 3, and I get 63. 9 times 9. I included that as one of my perfect squares, but let's see what the shortcut is. Take the second number and drop it by 1, and add 1. You got it. Are you getting it? Okay, there are different ways of doing this. There's a lot of things that are done with finger counting. Same idea. Now, what method did you learn?
They just put like 9 times 1 all the way through 9, and then they went 1, 2, 3, 4.
Yes, it's the same thing. That's the way it's done as a nightclub routine. And this is done as a nightclub routine. That's where I first saw it. So what's being done, you just write your numbers. Let's see, you start with what? Your 9s, 8, 7, 6, 5, 4, 3, 2, 1. And then this is 0, 1, 2, 3, 4, 5, 6. I did them backwards the wrong way. My apologies. I want to go the other way. Okay? Because what this does, 9 times 9, this is 9 times 10, and this is 9 times 9, 9 times 8, 9 times 7, and so on. So you just write them backwards and forwards, up, sort of one going down and one coming up, and you get all the answers. I agree, that's another way of doing it. But instead of having to write those all out, if I just take the 9 times 7 and drop the 7 to a 6, add 3 to make 9. What about 9 times 4? Does it work for something like that? That's 2a, 3, and add 6. Now, if you think of all the things that bother you in the multiplication table, for the most part, it's what? The larger numbers. 6, 7s, 8s, 9s. Well, we took care of all the 9s, some of the 8s and 7s. And the key is the shortcut for 9s and the perfect squares. That takes care of most of it. Before we leave this, just a comment, I'd like to extend your multiplication things that you know for perfect squares beyond up through 10. So keep in mind 7 squared, 8 squared, 9 squared, 10 squared. Those are usually part of what you learn. 11 squared is 121. 12 squared, that's the 12 dozen. 144. What was the name we gave for that number? 12 dozen business.
One gross.
A gross. Good. That's a gross. 12 dozen. When you order things, you often order them as a gross. The 13 squared, sometimes we throw in 169, but at least up through the 12s. I'm going to give you a shortcut for a number ending in a 5. We're going to use these right here for some things we do Thursday. These are squaring a number ending in 5, shortcut. Okay, so it's shortcut a number, let me say squaring a number ending in 5. Okay, this is the idea. So I'm just going to take something like 25 squared. That's squaring a number. Take the first digit, the 2, and multiply it by 1 higher. So you get 2 times 2. That gives you what? A 6, and put the 25 back. That's your answer. Okay. So again, 25 squared, I take the first digit 2 and multiply it by the next higher number. That gives me a 6, and I put 25 at the end. Let's try 75 squared. What should my answer be? What do I multiply? 7 times 8, what do you get?
56.
56, agreed. And then what do I put at the end?
75.
Not 75, 25. So your answer is 56, 25. We need to do one more. Let's try one more. Let's take 35 squared. What am I going to do? Take the first digit, which is 3 times what?
4.
3 times 4, agreed? That's the next higher number. So 3 times 4 is 12, and then do 25 at the end.
So they always end in 25.
Always end in a 25, exactly.
Awesome.
65 squared. Let's try that.
4225.
Very good. 6 times 7 is?
42.
42. I remember I'm getting this 42. I take 6 times the next higher number, which is 7. 6 times 7 is 42, and then put 25 at the end. And we're going to use that on Thursday to give us a little bit of an idea about when we can stop with some problems you're going to do over the weekend, which otherwise could take you a very long time. Okay? Any questions in this shortcut? Now, I want to indicate to you where we're headed with this. We are multiplying things together and getting answers, and the answers are called products. Now, if I reverse products, and by that I mean start with product and get factors. Now, a comment here, when we multiply two things together, we call them the factors. So when I say 6 times 7, remember I did that here? 6 times 7 to get the 42? The 6 and 7 are called factors. So if I start with something like 35, that's my product, and I want the factors I multiplied together. And you have a couple choices. But if I take the non-trivial case, it's 5 times 7. So we start with a product, and then you give me the numbers you multiply together. We call that factoring. And that's where we're headed Thursday. Now, we do put a little more into it than that. I want my factors to be prime numbers. And so it'll become a little more challenging than just finding any two that work. So, for example, if I give you something like 70, you could most likely be comfortable with this answer. 7 times 10. So I started with 70 and I wrote it as a product of two factors. But the 10 is something I can break further. And so I would write it as 7 times 2 times 5. And this is called now writing by 70 as a product of prime numbers. And that's where we're headed. Okay? But for the moment, I just want you to realize that we can go in two directions. You can multiply things together and get products. You can start with a product and you give me the factors that I would multiply together. I'm going to write a new word up here. Algorithm. Now, it is a process I use to get an answer, and I don't expect the person usually to understand how the process works. Let me show you an algorithm. So the algorithm for multiplying. And this is one that I suspect everybody's used in here. The one I usually illustrate here is this one. I want to talk about this for a moment. Now, the first thing to note, I lined up the 4 and the 2. I don't have to. That was done out of habit. I don't have to line up the ones column. But if you do, the algorithm says you take this 2 and multiply it by each of these digits. So I get an 8, and an 8, and a 2. Then I go to the next number, which is a 1. Now, what do I have to usually do? Many of you will put zeros. Many of you will put X's. Many of you will just leave a space. My training was, as a young kid, leave a space. I see a lot of books using X's, others putting zeros. And then you go to the 1 and say 1 times 4 is 4. 1 times 4 is 4. You have the 1 here. And of course, when you add, you carry, you get the 7 and the 1, and we say 1728. Now that's an algorithm. Nobody expects you to necessarily remember how you put that 0 in there. Or why. Now the answer to the question, why do I put a 0 there, is because this 1 represents the tens place. And so when you took a 10 here times a 4 here, you really had 40, so you make sure the 4 is going in the tens place. But you don't have to remember that. You can just use the algorithm. There have been other algorithms used in history. A lot of ways of doing multiplication. This is just the one that's currently used. The calculator, to an extent, is an algorithm. You don't know how it works. You press the buttons and you get an answer. Before I leave this, this is a rather important number for us. I'm going to reference something called a cubic foot. Now, you have heard about air conditioners and how much air they move. And they talk about cubic feet of air. And you've also maybe heard about older cars. The size of the engine is called number of cubic inches. And what do we mean by a cube? Well, a cube is like a box that has the same dimensions on every side. So if I have a 1 cubic inch ice cube, it's 1 inch by 1 inch by 1 inch. Now, most of the ice cube trays I see are rectangles, not cubes. But if you had a 1 by 1 by 1, it'd be 1 cubic inch. And we talk about large engines in cars at 400 cubic inches. Okay? That was a big engine before we went to the metric size. A cubic foot. Now, one of the things I remember as a kid is going to Labor Day picnics and making ice cream. How many of you went to a picnic or barbecued yesterday? Okay, on Saturday, sometimes this weekend to a barbecue or a picnic. Boy, it's so much for culture and so much for history. What did you do? You did homework, right? Okay, that's what holidays are for, homework these days. Okay, well, we barbecued, but in days gone by, when school didn't start until after yesterday, we used to have picnics, and you make ice cream, and you go to one of these, well, what do they call it? You put a coin in and a block of ice drops out. And I'd call it like a vending machine, except you got ice instead of Pepsi or coffee. And we used to have one over here on Caldwell Avenue. I don't know if they still do. You could go in, you put 50 cents in or $1, and you get a big block of ice. And then, of course, you'd have to break it up to put it into the ice cream maker, which you turned by hand, not electric. And you made homemade ice cream. Boy, I suspect maybe very few of you have eaten homemade ice cream. How many have? Oh, who did it for you? Your aunt, uncle, stepdad? You haven't turned the crank on an ice cream maker yourself and spent an hour in 110-degree temperature trying to get the ice cream to set up. You just haven't had a good picnic, I can tell. Now, let's take that block of ice, 1 foot by 1 foot by 1 foot, 1 cubic feet of ice. If you were to take a very nice saw and cut it into 1 by 1 by 1 inch ice cubes, this is how many you get. 1,728 1-inch ice cubes out of that 1 cubic foot of ice. So this is 12 to the 3rd power. 12 by 12 by 12. Very special number. Okay, that's an aside, and that's obviously not as relevant as I thought it might be. I thought all of you would have gone to a picnic yesterday, barbecued, made homemade ice cream, played baseball, softball, and you didn't. I feel guilty. We barbecued. Okay, Debbie, I'm going to go to the front. I'm just going to leave this on the board here, and I'll go to where you can run camera 1 on the space we have over there, because we need to look at problems that don't work this well. So I'm just going to do a very simple version of variation on what we just did. Don't want to do that one yet. That's not the variation, so let me clean it up just a little bit. Let me do a 2 here. 102. Same process, but we have to know how to handle that 0, correct? So I do the 2 times the 4, the 2 times the 4, and the 2. Then I'm supposed to, I'm going to put an X this time. Now here's what many of you probably do. And then do what? Is there a way of getting around that row of zeros? The answer is yes. So you could just put this 0 here and then do your 4, 4, 1 right there. Now if you like putting these zeros in, I'm not going to get upset with you. 1, 4, 6, 8, 8. But we can take a shortcut there. But this problem is going to irritate me if you do this one in a particular way. Okay, let's say I give you 1, 4, 4, and I want to multiply by 1, 0, 0, 0. You've got to use a shortcut here, folks. This will not be acceptable. This won't make it. That means you're asleep at the switch, you're just losing it. Here's what I want. Shortcut. Bring these zeros down, then multiply by the 1, and you're there. That makes a lot more sense. Now another way this problem might be written is this way. Because 10 to the 3rd means what? And if I'm blocking your view, just look at a monitor. 10 to the 3rd is the same as 1 followed by how many zeros? 3 zeros, correct? So I could just decide immediately to put these 3 zeros down and then put the 144. Works the same way. These are shortcuts. I don't want to see this when you can use a shortcut. I'll only give you half credit if you do this. Okay? I mean, you got a right answer, but you're working too hard. Okay? Any questions on that? Okay. What happens if I multiply more than 2 numbers together? We need to look at another one here. Let's say I give you this. What are you going to do with this?
2 times 7, 14.
Just do them you take them in order if you want, correct? So 2 times 7 is?
14.
The 14. So you do that. You still have to multiply by 5. The 5 times 4 is 20, carrying a 2. So that gives you 70. But if you do it that way, you're back to this. Well, what about mix and match?
5 times 2 is
Yes.
10.
If you take the 2 and the 5 first, that gives you a 10. Then multiply by 7, and isn't that a much easier problem? Agreed? Okay, so you do have a choice to mix a multiplication up, rearrange it in any way you want. Okay? And if you look through a problem, be cautious. Think before you start doing it. So for example, trying to think where I want to write this one, Debbie. I have managed to lock myself in. I'm going to do it down at the bottom here. Let's say I give you this. Now let me get out of your way. Just leave it there and I'll walk out of the way. Do you see the problem? What's your answer? The answer is 0. Because whatever you get for all these digits here, at the end you're going to get what? Something times 0, which is 0. Agreed? So look at your problem first before you just go ahead and start multiplying all that garbage out. 10 minutes later say, oh, geez, and feel like hitting yourself over the head or kicking yourself somewhere else. The idea is look at the problems carefully. Now, I think the problems start in 37, do they not? Will you turn to page 37? Now, in 37, we have that very important 30 problems. I'd really like you to be able to do them in 30 seconds, but realistically, a minute's probably more generous. So you have 30 problems in a minute. Now, your next 2 pages, 38 and 39. We have a few problems. They aren't as bad as what I could give you. I mean, I tried to be nice. They aren't 10-digit numbers times 10-digit numbers. They are reasonably small. I want you to use the algorithm or the shortcut, whichever is appropriate. You should try to take some time to review the shortcuts we took today so that they may become part of your background. I think you'll find them useful. You do need to do the lesson, the exercises, and then you go to page, is it 189?
Yeah.
Will you turn to page 189? This will be due tomorrow. This is review test 4. And I think you may find that on this review test that we're doing exactly what we did in class, some shortcuts, using the algorithm. I want it done without a calculator. Very soon our review tests are going to start spiraling back, reviewing some of the things we did earlier. So, today, lesson 4, tomorrow, lesson 5, Thursday, lesson 6. 6 is the biggie. We have a lot of work to do in 6, and you will have a lot of fun over the weekend.